Hi students, welcome back to the video lectures on sampling. In this video lecture, we will be discussing about discrete time processing of continuous time signals. Before going to that, let's see where we are right now when seen from what we wanted to cover in the beginning. So we finished basics of periodic sampling. In the next lecture, we have also finished frequency domain relationships of those sample signals. In the last lecture, which was in two parts, we did reconstruction of band limited signals from its samples. So in this lecture, we would be discussing about how do you process continuous time signal in a discrete time domain. So what exactly do we mean? So this is a snapshot of the DSP kits that you have used as a part of your DSP lab. This is not an exact the block diagram of that, but certain things are common. For example, take a look at mic in here, okay, line in. So you had, for example, to that you could give as an input the mic signal coming from the input mic, and it could do a processing there and then give it back again some, let's say, a denoised voice of it. Okay, so you could see here the input from the mic which you are giving to your DSP processor is a continuous time signal. Then it's a DSP kit, the whole processing is done in the discrete time domain. So there comes the codec part, okay, which is there on the top left corner. So that's something which does A to D and D to A conversions essentially. Okay, so that converts the signal from analog to digital. Okay, that gives you to multiplexer, and then you have the whole DSP kit 6713, for example. This is not the block diagram of your kit that you have used, but more or less the blocks, the bigger blocks would remain the same. Okay, you do a DSP processing, then again it goes back to the codec. That time when it reaches there, that's a discrete time signal, and then you finally again convert it back into the continuous time domain. So you could notice here, this is essentially whatever, particularly when you are dealing with a audio signal where you are recording something, giving it as an input to your DSP kit, doing some processing on it, and then giving back to your for example the speakers. You are giving that output to the speakers, so that your final output is a continuous time domain signal, your input is a continuous time domain signal, but in between what is done is a discrete time processing. So this is exactly what we will be going to discuss, but not of course how it is done here, but would rather discuss about the relationships between this continuous time the equivalent frequency response of what you are doing here versus the effect, the equivalent one in the continuous time domain. Okay, with that background, let's move on to some math of it. Okay, discrete time domain processing. So for that, let me go to the desktop sharing mode, and then let me go to this. Okay, hope the desktop mode is on, right? Okay, so this is what we would be going to do now, the discrete time processing of continuous time signal. This is what we are going to study now as a part of it. Okay, so let's first start with a block diagram, a simplified block diagram now, given that. Okay, suppose you have a signal which is xc of t. This is a continuous time signal. You would like to convert that analog continuous time signal to discrete time. You write it as A to D. Essentially this block you are mentioning giving T. Notice that by A to D converter, that block, we are representing both that multiplication with an impulse train as well as that integration part, everything. So as if the output now is simply x of n. That's what you got from there. So this, now you want to do a discrete time processing here. So you have a discrete time system here, to which you give this as an input, and then you got the output here, which let's call it as y of n, right? And you want the final output as a continuous time signal. So assume that again discrete to continuous time conversion you are doing. Let's call the final one as y is a continuous time signal, and of course you have to give here as an input again with for conversion or the sampling rate that you used for converting the signal. Okay, so if you look at this this whole thing as one block, suppose if you are looking it that way, the whole thing as one single unit, okay, this whole thing, then it's taking as an input, the whole box is taking as an input xc of t, giving you, taking a continuous time signal and giving you as an output a continuous time signal, isn't it? So let's call this this is effectively what it is doing. So h effective of, what should I call it? This is a continuous time domain, so let me call it as j omega. Okay, then this discrete time system, whatever the processing you are doing, let's call it as h of n here, and of course this would be equal to, its equivalent one in the Fourier domain is h of e power j omega. In this lecture we will try to answer or address two questions. First question is, when is the overall continuous time system is an LTA system? So when is the overall continuous time system, your continuous time system is an when is the overall system an LTA system? That's first question we would like to answer. Okay, when is that? Is it always for any given h of n, or are there certain things that we need to take into account? This is something at the end of this lecture we should be able to answer. And then another more important question, or equally important, how to design your h of e power j omega to achieve the desired h effective of j omega. See, what you are going to play with is in fact this h of n, so which means h of e power j omega, but you want, what you desire is, given an xc of t, you want a particular type of yr of t. So knowing that, how to design your h of e power j omega so that you get, or in other simple words, all we are going to say here is what is the relationship between h of e power j omega and h effective of e power j, h effective of j omega. That's how we could put the question. Okay, so let's split this problem into three sub problems. First, this block diagram. Let's see first the relationship between, let's say you have here as an input, okay, let me change this out. Okay, let's take this first part of your whole block diagram, where you had as an input here xc of t, you are doing some conversion, okay, and you are getting out of that x of n, isn't it? That's the first part. So let's first write the time domain as well as the frequency domain relationships between these two. So what can we say about x of n in terms of xc of t? That's nothing but xc of n times t. This is something first lecture we worked with it. So the second lecture we worked with the second relation in the frequency domain. h of x of e power j omega is equal to, we want to write it in terms of xc of t. Overall there is a scaling in magnitude by 1 by t. Okay, the moment you are taking samples, multiple copies of infinite number of copies are placed from minus infinity to plus infinity, xc of j times, well, the moment you are moving from xs of t to x of n, there is a scaling happening there by omega by t minus, okay, these copies are placed at omega s, right, multiples of omega s. Omega s is nothing but 2 pi by t, all integer multiples of that, which is nothing but 2 pi by t k, isn't it? Right. So we have written these are the relationships. This is the first class of your sampling. Okay, now let's go back to the second part where you give x of n, discrete time input, discrete time output, with the system response as h of n. Let's work out that part now. So you have a block whose impulse response is h of n. This x of n is coming as an input here, and as an output you are getting I of n. This is very simple, right? Let's write the time domain relationship. Y of n is equivalent to h of n convolved with x of n, isn't it? And the y of e power j omega is equal to h of e power j omega multiplied with x of e power j omega, isn't it? Right. So my convolution and then multiplication of in the frequency domain, right? Now let's take y of n as an input and something that reconstructs signal. This is the part 3. This is the lecture number 3 of our sampling. So now the block diagram for it, if you want me to draw, that's something. Okay, well, takes as an input your y of n, and what you are getting out of it is yr of t. Okay, we had written in fact that as hr of t, if you recollect the previous couple of lectures, part A and part B of your third lecture. So how did you write yr of t here? So your yr of t, do you remember? At integer values, it is its value is determined by the corresponding y of n, and non-integer values the sinc function was interpolating things. So that's varying from yr of t is n varying from minus infinity to plus infinity, y of n into sine of pi by capital T into t minus, this will be placed at nt, right, shifted ones, and then divided by sinc function. So you had pi by t into t minus nt. If you don't remember this, please go back to the previous lecture. And what about the relationship in the Fourier domain? So yr of t, what should I write here? For example, I want yr of j omega. Okay, so of course hr of t, for that I would get hr of j omega multiplied with y of e power j omega, but we know that that omega t is equal to small omega. That's how the relationship is there. So you would get here e power j times omega t, isn't it? So this is equivalent to low pass filtering. If you recollect, that's what we were doing, is a low pass filtering here, correct? And then we also worked out for this the limits would be from minus pi by t to pi by t. Okay, what was the value here? Do you remember that? This is t. Okay, and what is it that we are drawing? hr of j omega. Okay, and this is your omega. Okay, so if you want me to write here the value here, this would be, in fact, I should write it as t times y of e power j omega t, when your omega value is in between minus pi by t to plus pi by t, and of course its value is 0 otherwise, right? So that's individually the blocks. Okay, so we worked out first this block, we worked out this, then this, then this. Now let's try to concatenate everything and get relationship between yr of t and xc of t. That's what we will do now. So let's again start from the back here. yr of j omega, for example, we start here, yr of j omega, we have written it as hr of j omega times y of e power j omega times t, right? Now what is y of e power j omega t? Where do we get that? You get it from this relationship. So that's, hey, omega t, again omega, this is the relationship we have. So h of e power j omega t into x of j omega t, that's what you could write there. So this is equivalent to hr of j omega multiplied with h of e power j omega t times x of e power j omega t. Okay, and what about x of e power j omega t? That's the first module. X of e power j omega t, here again small omega replace with capital omega times capital T. That's whole thing you replace here. This anyway then will become omega. This would become their omega in that case. So what do we get here? All those copies would be there. So that's equivalent to hr of j omega times h of e power j omega t times, okay, 1 by t time, okay, times k varying from minus infinity to plus infinity xc of j times omega minus 2 pi by capital T times k. Wow, so very big expression you got here. This is how, if you notice, the output frequency spectrum in terms of the input frequency spectrum, we are able to write it. Okay, now, well, just now we have seen this part, is we know it, right? This is in fact equivalent to, what is its value, is t. So that's basically is this one, right? That's equivalent to t when absolute omega less than or equal to pi by t, right? And of course 0 outside. In other words, this whole expression has a value only between minus pi by t to plus pi by t. Okay. The first question that let's try to answer is, when will this be an LTI system? Okay. We are looking at a sufficient condition for that, which is of course not the necessary condition. The sufficient condition that you would, when this would be an LTI system, is your there is no aliasing. No aliasing. Where from is this aliasing coming? Where could this aliasing come from? Well, this expression, right? Okay, that's what we would consider here. When is that there is no aliasing actually? Well, your omega s should be greater than, omega s is nothing but your 2 pi by t. Okay, this should be greater than or equal to 2 times omega n, right? So hope you remember that. Omega s, omega, okay, I should have drawn it a bigger one. You have omega here. Okay, now let's assume this is your xc of j omega. Simply xc of j omega is this, but if you are trying to plot the summation of shifted versions of it, then as long as this is, there is no aliasing, so this, what would happen then? Well, when it is equivalent, then see, one more thing you notice here is, let's say you are keeping a copy at omega s, which is equivalent to 2 pi by t, but if you are keeping anyway this value is going to be 0 because you are multiplying it with HR of j omega. So when there is no aliasing, this pi by t, okay, so that you could see then, of course, without aliasing, well, the copy should be of same size. That was a mistake. Okay, it's too bad. Okay, assume again this is at omega s. Okay, so the closest case where there is still no aliasing but highest value of t is at pi by t. That would happen. Okay, this would be at pi by t. Similarly, this side you have similar stuff here. Okay, this is minus pi by t minus 2 pi by t. Okay, this multiplication is allowing you only this region now. So as long as there is no aliasing, this picks you only one copy, and that copy is nothing but xc of j omega out of this, right? The other copies will not be picked because of hr of j omega. So that means when there is no aliasing, because of this, I could write yr of j omega is equivalent to hr of j omega is t here. Okay, let me then write first this 1 by t. Let me write it first, 1 by t, and what else is there? H of e power j omega t. Oops, this got closed, but let me open it again. Okay, almost all things are there except the last one. This is 1 by t, h of e power j omega t, correct? H of e power j omega t. Notice here only the copy which is there at omega, this for k equal to 0, there is only one copy that gets selected. The rest anyway will not be there because hr of j omega is 0 for it. So I could simply write here xc of j omega. Hope you are following. So what did I get here? My yr of j omega equal to h of e power j omega t times xc of j omega. Very, very important relationship. Okay, now can you say just by looking at it, is it an LTI system or not? Indeed an LTI system, because you simply multiplying with h of e power j omega is giving you this. So what I could write now, my h effective of that implies this is an LTI system in the first place, right? And your h effective of j omega is equal to h of e power j omega t. This is giving you the relationship between the frequency response of the discrete time system and the frequency response of the equivalent frequency response in the continuous time domain. A very important relationship here. Okay, well, if you have closely noticed, I mentioned that this is a sufficient condition, okay, but always it's not necessary that there is no aliasing. To understand that, you should be looking at here. Sometimes despite aliasing, this could help you. For example, assume that your h of e power j omega is a low pass filter. You consider a low pass filter here. Okay, assume that you want to do a low pass filtering, but in this case you want to do a low pass filtering using a discrete time system. Okay, you want to do a low pass filtering of a continuous time system using a discrete time system, if you want me to more complicate that sentence. Okay, so what I mean by that is, assume that my h of e power j, this is, okay, let me write here, this is an example. Now we are working out. Okay, assume that your h of e power j omega is an ideal low pass filter, let's consider, whose value is 1. Okay, and let's take the cutoff frequencies at omega c. 0 otherwise, right? So let's first plot h of e power j omega. How does it look like? This is my omega. Okay, I'm going to plot h of e power j omega. Its value from omega c to minus omega c is 1, right? And where is the next copy placed? Of course at 2 pi, and here minus 2 pi, and so on. Okay, this is my h of e power j omega, right? Now what would be the h effective of e power j omega? So you know that the relation here is capital omega t times capital T is equal to small omega. H effective of j omega is equivalent to, now here I move from omega to small omega here. So that relationship is, so this is nothing but your h of e power j omega, where your omega is equal to omega, yeah, omega t equal to omega essentially. Okay, so so this, of course you have this relationship being your omega t equal to omega, right? That's what your r, since that variable is omega, let me write it here in the other order, your omega equal to capital omega t. Okay, so let me draw that out. Now what do I get here? My axis is capital omega, so that means to get that you divide it by t minus omega c by t, and this is omega c by t, and of course this is still 1. There is only change here, and that's giving you h effective of j omega, right? You might be wondering, I should keep the copies of it in the other places also. Yes, in fact I could do that. There is not really a problem. I could keep the other copies. For example, if you want to keep, I could in fact at 2 pi by t, I could draw the same thing here, minus 2 pi by t, I could draw it out. Okay, that's not a problem. Why is it not a problem? Because anyways here when I get yr of g omega, when I'm having this hr of j omega, that would anyway cancel out the other things because this is there here. But the way they conventionally write is they slightly modify this relationship. So how is it usually written is this: h effective of j omega is equal to h of e power j times omega t only for magnitude of omega less than or equal to pi by t. That's what it is done. Okay, again assuming there is no aliasing there, and they will make 0 otherwise. Again, this is a convention, not necessarily required, because even if it is not imposed strictly, later this h of this hr of j omega will take care of it, but this is the convention, so let's follow that. Okay, this is what we have it. So this is your, so I'm not drawing this, I'm making them 0, but if you, it's up to you, I leave it to you. Okay, so two interesting things anyway, since we have done this low pass filtering here. Suppose I want to do a low pass filtering in the continuous time domain using discrete time domain. What should I do? I should know the cutoff frequency values here. So what is my cutoff frequency here? If I call it as omega c, the cutoff frequency, omega c by t, right? Of course then plus or minus omega c plus or minus omega c by small omega c by t. So how could I vary omega c? There are two possibilities. I could either change the cutoff frequency of my discrete time filter or change the rate of sampling. This is a very interesting thing. The same filter, discrete time filter, can be used effectively as if it's a low pass filter with varying cutoff frequencies by simply changing the sampling rates here. The sampling rate T here, and of course that's T is same here. By simply playing with that, you could in fact make it as you could vary the cutoff frequencies of the effective system, of effective continuous time system. Anyway, that's just a detail springing out of this problem. Okay, hope the concepts are clear to you. So this is so the whole most important thing is H effective of j omega, as this is the result. Okay, then well, let me come back to just one point I have left. As I mentioned, this is a sufficient condition, not a necessary condition. Okay, even there, suppose there is an aliasing. Okay, this h of e power h effective of j omega, you will be multiplying that, you see here. Okay, you will be multiplying with xc of j omega. So even then, even suppose, even if there are some overlaps happening here, suppose in this specific example you could still work it effectively, because assume that your xc of j omega is something like this. Okay, if it is something like this, well, I should have plotted it here. Okay, let me plot it here, then there. Okay, let me just remove that. Let me go back. Oops. Okay, so assume that I have my xc of j omega is something like this. Even when you are placing copies of it, okay, it should be again here, copies of it here with aliasing, this low pass filter will anyway make sure that now that low pass filter would give me something like this, right? So still it acts overall perfectly fine as if it is an LTI system. Again, this is how it works when you have a low pass filter there for h of e power j omega. So you could see, despite that condition being satisfied, there could be instances where this will work out. Okay, again, these are all special cases. Okay, so that's why we mentioned it as a sufficient condition. If you don't understand this necessary and sufficient condition, when despite that not getting satisfied, when is this working, don't worry about it anyway. Okay, so if you understand the rest, it's fine, right? So with this we are done. So before we wrap it up, let me give you an exercise problem to work it out, to make sure you have understood things. Okay, so in this what we do is we will do an implementation of low pass filter we have worked out. Now we will do implementation of an ideal continuous time band limited differentiator. Continuous time, okay, band limited differentiator. So this example, let's work it out. So for example, you take this relationship. What we want is your what I want is let's say the yc are reconstruct, we are talking it as yr. So let me write it as y subscript r of t is equivalent to the derivative of xc of t. This is what I want the relationship. Okay, I want to achieve it through a discrete time system. So for this to achieve, I want you to compute what is the h effective of j omega of this system, right? And for that, within that, suppose if I am doing it through a discrete time processor, okay, of response h of n and h of e power j omega, what should be that? The frequency domain. What should be that in the time domain? You compute these values, and I want you also to draw then magnitude, okay, magnitude and phase plots of h effective of j omega and h of e power j omega. Hope these things are clear to you. Okay, let me go back now. Right, so that's all for this lecture on discrete time processing of continuous time signals. I'll stop here, go through it carefully, and if you have any questions, you could post them in the comment section, or else you could get them clarified during a Zoom session also. Okay, I'll wrap it up with here. Okay, see you in the next class. Thanks for watching. Yeah, take care. Bye.